for delta KE in that problem. We're usually looking, God bless you, for delta KEM.
So is that initial minus final?
Final minus initial.
Minus.
Always. Just like think about delta V earlier in the year. It was final velocity minus initial velocity. And the same thing applies to the momentum impulse theory. Right? See the delta P up there, Em? That delta P is final P minus initial P. It's important that the order is in the correct order because then the force is negative or positive as a result of the order of the subtraction. So we have to do final minus initial. Yeah?
So for an inelastic problem, the momentum is staying the same throughout the beginning and the end, but
the energy is not.
Changing.
Correct. Whereas elastic, the energy the system has to start will be the energy the system has to end. Again, there will be no energy loss in an elastic collision. Hey, tomorrow, just remind me, you guys have a double, right?
Yeah.
Okay, so I'll give you the first period to finish up that lab that we never really got a lot of time for. So if you haven't finished it yet, you can. If not, if you've done it, that's awesome. Seriously, it's good. And what you can do is you can study, you can do practice problems in the first period. Because you guys have never had an opportunity where you had a double at a test. The other class has, though. So I'm going to give the first period for you to, actually one of the time you did, but I gave you the test in the first period. And the reason I did it at that time is because you were even with periods with the other class. But technically, you guys are a period behind the other class. You haven't had a chance to work on that lab. So if you want to work on that lab or just practice problems in the first period tomorrow, but don't think of that as a fail-safe, like, oh, I don't got to study tonight. I'll just ask Hal all these problems in the first period tomorrow, and then I'm good. Yeah, that's great. Like, study tonight still. But if you want to finish up your lab or do a little bit of that work, you can. By the way, I gave that lab out, not yesterday, but the day before. 3 people, I think, were out. Who was out?
Me, Bridge, and Spencer.
Okay, that's why I'm like, I have 3 copies of the lab. They're up in my office, so come by to get it at some point today, okay? I'm thinking about that today. I'm like, why do I have 3 copies? I knew somebody was out. All right, so let's jump into the momentum impulse theory for a minute. Something that seems to not confuse people, but can be a bit difficult compared to the other stuff that we've studied. So the momentum impulse theory, first, it tells me, you know what? If an object feels some sort of a force on it, it's going to cause a change in motion. I know that already. How come I know that already? How do I know that already? Because it's moving, good. But earlier in the year, I mean, Alex, like earlier on in the year, what tells me that if there's a force on an object, it's going to change its velocity?
Acceleration?
Good. That's the definition of F equals ma with acceleration, right? We use Newton's law, F equals ma, to tell us, well, you know what? If an object has some sort of an unbalanced force, it's going to have acceleration, and acceleration is a change in velocity. Well, that's what this is telling us as well. It's telling us that there's also a change in velocity occurring. Is there really no Alden in this room anywhere? Is there one over there easily that I can plug into while I stand for a second? Awesome. Nice. I'm going to have to stand over here, so just look at either screen. So, I know, guys, I shouldn't be doing this. I apologize. I didn't think I had very little battery. So, when we look at a problem like this, we have to think to ourselves, at times, the momentum may not change. And if the momentum doesn't change, if the change in momentum doesn't change, like for 2 scenarios. So imagine, like the example we did in class, we've talked about now a couple times in your problem set, it was with the airbags. But I talked about the gymnast example or the catching a baseball at a stadium example. So you throw a baseball with a certain velocity, say 70 miles per hour. I'm going to use miles per hour because I'm not going to do the math for this. I'm just going to leave it as miles per hour. And at the end, it's got 0 velocity because you catch it. You do it again. You throw it 70 miles an hour. And this time again, you catch it. So it also stops it. So it looks at right away, it's the same scenario. Why am I writing it twice, right? So here's the difference. In scenario 1, you simply take your hand and you stick your hand out. And the ball just smacks your hand. And it stops instantly. Still the same starting velocity. In scenario number 2, though, instead of doing that, you go ahead and you take your hands and you kind of cradle the ball as it's landing, and you catch it with a little bit of a soft hands effect. If you don't know what I'm saying, try to look to what I'm showing right now. So you kind of like catch it like this, right? So you cradle the mass as it goes toward the body. So these 2 scenarios are very different because of the way you catch it. But the change in velocity is not different. Does everybody see that? You're going from 70 to 0 in both cases. So if I think about my definition of momentum change, this is really final minus initial. And if I think about it this way, the object isn't changing. It's a baseball or a ball or whatever, a mass the whole time. So M is not different. So in both of these cases, this is what I've got. So in case 1 and case 2, I've got the same delta P. I've got the same delta P in both cases. The object goes from, again, 70 to 0, and its mass does not change. So delta P doesn't change in case 1 and case 2. So that's a constant. So I want you to think about this or jot down that this is a constant right here. Delta P is your constant. It's not changing. So if suddenly I cradle the object, I'm increasing the amount of time that this interaction is occurring for. I'm increasing the time period that I'm taking to catch the ball. So if I do the math real quick, I'm not going to put numbers down, I'm just going to use general values. Let's say that delta P is 100, and that equals F times T. And let's say you catch it in 0.5 seconds. Okay, let's say you catch it in 0.5 seconds, it just slaps your hand, the first case, this is case 1, and the change in momentum is 100. It's whatever number it turns out to be. My answer for the force felt would be 200 newtons. I'll take 100 divided by 0.5, which is 200 newtons. And that's for case 1. But for case 2, the same 100 occurs for the change in momentum, but in case 2, again, I catch it with a little bit of a soft hands cradling action. So instead of taking a half a second to catch it, I catch it over a time period of, say, like 2.5 seconds. So my force in this case would turn out to be around 40, or actually exactly 40 newtons. So look at the difference in the force felt. That's the important part of this problem right here. If an object slows down real quick, and you feel this in the car, you guys have noticed it. If your parents, I'm sure at some point in time, have slammed on the brakes just like to save you, or to save the car from crashing, it happens. People drive like maniacs, not your parents, but other people a lot of the time, and then you have to like slam on your brakes. So imagine this happens. If you get the brake slammed on, you physically feel the force on your body jolting forward, right? On the brake, on the subway, you feel it all the time. But if the subway conductor lightly presses the brakes, you don't feel it as much. You come to a slower speed at a longer time period. Same thing happening here. Suddenly, we increase the time period from 0.5, which is a half a second here, to 2.5 seconds. So the time period went up by a factor of what? What did the time period go up by a factor of, Chris? What is it?
5.
So what did the force go down by a factor of? Look at the force from 200 to 40. What's that factor? It's also 5. Remember, factor means divide the 2. So if I go up here from 0.5 to 2.5, that means I'm multiplying by 5. To go from 200 to 40, I'm dividing by 5. So an increase in the time that this interaction is occurring causes a decrease in the force felt. A decrease in the force felt. So again, it's the same example if I were to jump off this countertop here and land on the floor. I would not land on the floor with my knees locked, because that collision, that impulse that my body would feel, the impulse, would act for like a split second. But if I jump off the ledge and I land like this, and I bend my knees when I land, I'm absorbing the shock. We call it absorbing the shock. What am I doing? I'm increasing the time period, and thus decreasing the force acting on my legs. So how might these problems occur mathematically? How might these impulse momentum, because this is an older one that we haven't done in a while. How might these occur? You might start with this. And if it's a multiple choice and it says, the force applied is 200 newtons for a time period of 1 second, what's the change in momentum? It's at first like, oh, I don't have anything about mass and velocity, so I can't find change in momentum. But if you're given F and T, plug them in. Remember, this is called impulse, and this is called change in momentum. Okay, we have impulse and we have change in momentum here. So if you don't have the change in momentum, but the problem asks you for it, you may be able to figure it out by finding the impulse, F times T. And that absolutely works. And vice versa. If you can't find the impulse because you don't have F and you don't have T, instead you could find the change in momentum if you know the mass, the initial velocity, and the final velocity. So it depends on what you're actually given and what you're asked for this equation to be manipulated. If I'm given if I'm given the mass and all the velocities, and I'm given the force, and I want the time, then I need to use this equation, which simplifies further, again, like we just wrote on the previous slide, into this equation. So there's not one right or wrong answer for the question of which of these forms are we going to use. But we need to know that the starting form is the one at the top. Delta P equals Ft is what's given on your formula sheet. So if you're trying to find change in momentum or impulse, you could possibly use that first one. But if you're given masses and velocities and the time, or masses and velocities and the force, or if you're given pretty much 3 out of 4 of the things, you're going to use that last formula on the bottom. You could also be given the initial and final momentum, and then you would use the middle formula right here. If you were given initial momentum and final momentum and asked to find time, if you're given, say, the force. Okay, so there's a lot of opportunity for this equation to be presented on the test. Whether it's multiple choice, short answer, or mathematical, momentum impulse theory is like a chunk of this test. It's like a quarter of the test in your mind. Okay, it's a lot of your test material when you think about that. And it will show up in all those 3 areas. It will show up in all those 3 areas. All right. Conservation of momentum we've done a lot of lately. We've done material with change in kinetic energy. We started off the chapter with just basic momentum. Let me open up the floor for questions at this point that you might have. If you want to ask on, whether it's problem set or even the review document that I put on. I put like a 7.1 to 7.3 practice questions on Moodle on the documents and handouts. You can check that out tonight if you wanted to get a little extra review. I put that up like a week ago or so now. I actually forgot that I made that visible. Gigi mentioned it yesterday. So you're talking about the document? I forgot that it was there, but it's a good opportunity if you want to look under documents and handouts for some practice questions. I'm not saying they're going to be the same difficulty exactly, but they're a good example of what you could expect, type of. Chris, and then Tom?
Do you put up the problems and solutions
Only if everybody turns them in, which has never happened. So this year has never happened so far.
Really?
No, there's never been a problem set where everybody. That's why you notice Steve checks off your problem sets. I have him do that. So if everybody turns the problem set, I put the solution up for that problem set. But this year it has never happened that everyone has been on time.
Or just for class?
I mean, it's on Moodle, so it's got to be those sections. Think about it. Yeah, I mean, it is annoying. If you get to the point where you struggle on one question and you want to know how to work it out, and you look at Slater and the explanation isn't really clear, and you want to come talk to me about it, you can do that. That's fine. Or I can send you my version of the solution, which is right out of the textbook. It's just the textbook has a generated solution for all this stuff. Or I can honestly work with you on that problem if you really don't understand it after already looking at it. But yeah, any of those problems, Chris, you want to ask about, you can. But I only put the solution up if everyone turns it in. Tom?
So, difficulty-wise, compared to our last test, how would you say?
I think it's less difficult because of the fact that it's the same ideas. Conservation of momentum is like conservation of energy. Using kinetic energy, again, used the last chapter. So personally, I think it's easier. But again, I mean, my opinion is not really something that, as a physics teacher, can be taken lightly, right? So, yeah.
Do you office hours?
Yeah.
What time is that?
The school ends at 1:15, I guess, right, today? So, like 1:20, 1:25? It's a C day? Pretty much after it's over. Yeah.
I just have a question about the sheet and worksheet.
Yeah.
Number 6.
You might have.
All right, so we're talking about the worksheet. Listen. Worksheet, this is part C. Can you tell me what it says by any chance?
Suppose you are traveling in a bus at highway speed on a nice summer day and the momentum of an unlucky bug is suddenly changed and splatters over the
You can't, yeah. Can't hear it now. It's just there's too much noise out there.
Alright, suppose you are traveling in a bus at highway speed on a nice summer day and the momentum of an unlucky bug is suddenly changed as it splatters onto the front window. The part A says, compared to the force that acts on the bug, how much force acts on the bus? More, the same, less, and why?
Okay, so this is a good question. Brings us back to Newton's laws, actually, really. So when I think about this, the bug has very little mass. Very little mass. The truck has a lot of mass. Now, when two things collide, the change in momentum that each of them experience are the same. The change in momentum for each is the same. When two things collide, delta P for these objects, for object 1, is equal to the same delta P for object 2. If I lose momentum, where does it go? It goes into the object that gains it. So because the change in momentum for these objects are the same, and because of that, we know that Ft must be the same also. And the reason we know that is because change in momentum is defined as Ft. So I'm simply replacing this with its equivalent formula. Now the bug smashes the windshield for the same time period that the windshield smashes the bug. So the times are also the same. So time cancels out on both sides. When time cancels out on both sides, I'm left with the fact that F1 equals F2. And that's Newton's third law. Okay, the bus and the bug feel the same force. It's just that the bug has much less mass. Because the bug has much less mass, it feels a greater acceleration. That acceleration smashes the body to pieces. That's physically what's happening. That was part C of number 6.
Yeah, so they got to say full. That was 6A, and then 6B is the end question.
So this was 6A from the worksheet on Moodle.
Yeah.
Do you want to ask another question for me?
Yes. And it says, although the momentum of the bus is very large compared to the momentum of the bug, the change in momentum of the bus compared to the change in momentum of the bus is the same. Why?
So the rationale for this is that momentum is always conserved. The law of conservation of momentum tells us that if something gains it, the other has to lose it. So there's no physical explanation for it. It's using the law of conservation of momentum that gives you that idea. Just like the energy concept. If I lose kinetic, where does it go? It's got to go into potential or work done by friction somewhere else, right? So if I lose momentum, where does it go? It goes into the bug. So the change in momentum, the magnitudes are the same. I would have a positive change, and the bug might have a negative change. Well, in this case, the magnitudes would be opposite. Yeah, they would be opposite of each other. One would be positive, one would be negative. Yielding 0 if I add them together. So if I lose 5 in momentum and they gain 5, add those up, you get 0. There's no change in the system. But yet each object changes individually. Problem set questions, concerns you had when working on the problem set. Homework, yeah.
I have a question with the problem set. 93, I believe, on page 261. So I got the right answer and everything, but I was just wondering how when you get like because obviously it's gonna be sometimes you get like a negative value. Like for this one, it's like 27.9 equals negative 0.89 m2. So you want to divide to find the mass. Do you get the absolute value of mass?
So mass needs to be positive. So there's a mistake somewhere
That's a
along
mistake.
the way.
Okay, so you know that that's a mistake. Okay.
Was it an impulse momentum problem or was it a conservation of
It was
momentum problem?
PI equals PF.
Yeah, conversation.
Yeah.
Conservation? Conservation? So if it's conservation, it means either you move something wrong on one side of the equation, or you forgot a negative sign for a velocity somewhere.
Oh, I think I get mixed up with the negative and
Repetition.
Maybe that. But if it's, listen guys, listen. If it's momentum impulse theory, and you get a positive force, but you know that the force is slowing the object down, it means that you probably forgot to have a negative sign, or you did, pi minus pf instead of pf minus pi. Remember I talked about the order mattering? So when you get a negative answer or a positive answer for force, it just indicates that the force is positive or negative, pushing or helping or against it. But time has to always be a positive answer. Time and mass will always be positive answers. Time and mass. Right?
Yeah, we go over 91.
Same page?
Yeah,
Or around that area?
261.
Do you have the problem by any chance?
It's like
I don't have the
something
text.
about astronaut.
Oh, okay. So this is an astronaut stranded in space. The astronaut wants to move back to his ship or her ship. And he or she does not have any sort of propulsive method. You would need like a little rocket booster to propel you backward, right? So instead, the astronaut throws a wrench. The wrench gains positive momentum. So what must the astronaut gain? Negative momentum. Because the positive that the wrench gains in momentum is equal to the negative the astronaut gains in momentum to balance out to zero again. Because the object and I'm an astronaut and I have a wrench. I'm standing still. What's my overall momentum? So if I throw the wrench and it has positive, I gotta have negative to balance out to again be zero. Because conservation of momentum. So yeah, that's the idea that you throw it forward, you get propelled backward. You can use Newton's third law to explain that too. You apply the force that way, it's going to apply force backward. Remember,
Equal and opposite reaction.
remember that momentum impulse theory is the exact same thing as F equals ma actually. I can quickly show you that in case those that are confused about that. Take a look. Take a look at this.
What would be the best way to do that if you're actually in space?
You would do exactly that.
Like throw it as hard as you can, or like slightly push off it.
Well, it depends on how fast you want to propel yourself to the rocket. So you'll make it back there because there's no friction in space. So you could literally just do this, Chris, like lightly push it, and you'll move real slow back to the station and make it there easily.
But I feel like if
You throw it
threw
fast.
I feel like if you threw it, you wouldn't have that much.
You wouldn't because the mass of the wrench is so little
So
that you probably still could throw it physically. Yeah. Hey, take a look. That's why momentum impulse theory is F equals ma. It's the same thing. Delta V over T is A, right? This right here, this is really acceleration. So if I think of momentum impulse theory, I can rewrite it as F equals ma. It's the same thing. But I will tell you this much. For a math problem on the test, I will absolutely ask you to do it using momentum impulse theory. The midterm, you could choose F equals ma. You could choose delta P equals ft, either one. But on the test you take tomorrow, I will write in words, using the momentum impulse theory, determine, and then you find the determining values. Is that clear what I'm saying? So you're not using F equals ma tomorrow, because this topic is what I want you to learn about, which is momentum. Yeah, Daniel.
On 261, 80,
I don't have the book, but if you tell me about it, I can... Anybody have the problem in front of them? I can read it. Daniel asked about this problem. We don't have the problem in front of us now. 261, number 88. Anyone have the words written already? Yeah, go ahead, Bridge.
A system consists of two objects. If the total momentum of the system is fixed to zero, does this mean that the momentum of each object must be the same?
So, if I gain, you lose. That's all that matters. So each object doesn't have to be the same. So I can be a bus traveling down the road that's getting hit by rain. The momentum of the rain is altering the momentum of the bus, but the system of rain and bus becomes zero. So every time the rain hits the windshield, it's got positive momentum. What is that going to do to the bus? It's going to lower its momentum. Its change will be negative. The momentum from the rain, the loss of momentum from the bus, will cause a net of zero. So the system's momentum will never change, but each object can change, and they would change in opposite fashions.
as long as it equals to the total momentum.
Which in this case could be zero or whatever you started with. So an object moving with 10 kilogram-meters per second will always have that much momentum. So if snow is piling on, or if it's burning rocket fuel and stuff, it's going to change, but the object system will not, the whole system will not change, just the object individually.
So basically, the momentum is transferred between the two
Yeah.
objects?
The loss of one becomes the gain of the other.
Okay.
Yep, it's a transfer.
In the problem where like the soccer ball has the wall, it says that it deforms and
That deformation that occurs makes it an inelastic collision in the wall. So if you want to find the delta KE for a problem, guys, you can see how much energy is lost in the deformation of the wall.
Bye, Mr. Howell.
It would be inelastic, yes. It's a different type of inelastic. It's not the inelastic where two objects are fusing together. Follow what I'm saying?
Daniel, I'm sorry
It's like an inelastic where energy is
Thank you.
internal energy objects are changing everything. I'm not going to go crazy.
What do we have?
Okay.
302.
You're welcome. Don't forget, Spencer, Fran, and Bridge. Your labs are upstairs in my office right now. Unless I have them down here, actually, I can check, but I don't think they're down here. me check the window and see.
Mr. Alex, trying to write email us.
I'm gonna email you, Chris. Let me look at the schedule. If I don't, for some reason, though, email me. Okay? But I'll look at your schedule. Yeah, upstairs. Yeah, I mean, I teach in this room this period, and then I'll be up there 7 days a period. Okay? Or just come by after school. Any period's fine. And you're coming 7 period. No, if it is, we'll go somewhere else. Yeah, you can walk into the room and check the schedules inside the room. Alright? No problem.
I'll review. Hey, Derek. Hey, Derek.
No hard copies for other sessions. Only one hard copy for the project. I'm like, wait till they're all here. They'll take some notes.
It's
too
Yeah.
Only one.
I can't lie.
Alright, I expect my freshman to come. Nope. Alright, you want to check with them real quick? Unfortunately, I'm going to be presenting from this side. Yes, I've been so sorry.
Hard copies are you going to buy? Hard copies, but any hard copies.